Okay, let's review indefinite integrals, which are antiderivatives. This first one's tricky because the square root of x is not a common function, and we need to realize that that can be rewritten as x to the 1/2 power dx, and then I can use the anti-power rule on that. So if I antiderive that, add 1 to the exponent, I get x to the 3/2 divided by that new exponent, except I don't like to divide by a fraction and multiply by its reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. And remember, got to go to the ocean, plus c. So the antiderivative of the square root of x would be 2/3 x to the 3/2 plus c. Let's take a look at the next problem. And this one has an inside function and an outside function. So this is an anti-chain rule problem. So remember, I got to antiderive the outside. So that'll be 1/5 to the 5th power with respect to the in divided by the derivative of the in. Well, if I go back up here, the derivative of 2x plus 3 is dividing by 2. So even though I say in my head dividing by 2, I multiply by 1/2, and again plus c. Next one, this is another tricky one because 1 over x squared, we haven't learned how to antiderive fractions. We will certain types of fractions, but this is not one of them. So the trick here is, again, is to rewrite this as a problem where I can use the anti-power rule and realize 1 over x squared is the same as x to the negative 2. So now that I've rewritten it, now I can find the antiderivative by adding 1 to the exponent, so x to the negative 1, dividing by the new exponent, which will just make that negative, plus c. And so it's negative x to the negative 1, which could be rewritten as negative 1 over x plus c. Either answer would be acceptable, though, however. Okay, last problem here is 8x to the 1/3 power. So a little bit tricky because you got to anti-power rule this, but you got to deal with a fraction. So when I add 1 to the exponent, I get x to the 4/3 power. But now I need to divide by that new exponent. And remember, just like the first problem, dividing by 4/3 is not recommended. So we're going to multiply by 3/4. So I'm going to multiply by 3/4, but remember, I have the 8 out there. So I got to multiply the 8 times 3/4, and again, plus 3. And this becomes 6x to the 4/3 plus c. And so there's my answer to that particular indefinite integral, or remember, antiderivative. Okay, so here we're given a moving object whose velocity is described by 55 plus 12t to the 0.6, and that asks us to find the area between t equals 0 and t equals 2. And so if I look here, I graph the function, and that's what the graph looks like. But we're only going to look at it from 0 to 2. So we're only going to look at this part of that graph. Okay? So the trick here is to actually imagine using a Riemann sum or a rectangle to actually come up with the area here. Okay? Get rid of this for a second here, and I'm going to actually draw a little narrow strip inside this problem anywhere I want. Doesn't really matter where I put it. And I'm going to label the point up here. Remember, my x-axis here is actually t, and my y-axis is actually v for velocity. So that point up here is going to be t comma v. I'm going to use that to find the area of this rectangle. Well, the area of this rectangle has a length of, we're going to call this width dt, because the variable is t. So it has a width of dt, and a height of the y value, which in this case is v times dt. Then I'm going to imagine drawing a bunch of these rectangles all throughout the region and fitting that in to actually estimate the area using Riemann sums. Well, the symbol we use for that is this. This is Riemann sums of v times dt from t equals 0 to t equals 2. This is notation that sigma means take a Riemann sum. But that will not give us an exact answer. An exact answer requires us to have an infinite amount of rectangles. So to get an area of an infinite amount of rectangles, this is where we use the fundamental theorem. We change that Riemann sum symbol to the infinite symbol, which is that elongated s, and we're going to do this from 0 to 2 of v times dt. Okay, so this is the process of the area of one rectangle, the area of a bunch of rectangles, and eventually we're going to go to the area of infinite amount of rectangles. This last step will give me the exact answer. That's a nice thing about this. So because of that, we actually usually skip over this middle step. I'm going to make you do the middle step just for the next assignment or two, but then we're going to actually skip to this last one because it will give me the exact area of the curve. And I show you how that works here. So remember, if we want to do an infinite amount of rectangles, it's the integral from 0 to 2 of 55 plus 12t to the 0.6 times dt. The v here is the equation that was given to me in the original problem. So now I have the skills necessary to be able to actually antiderive this, plug in the two bounds, and subtract. So I'm going to antiderive 55 and realize that's 55t. I'm going to antiderive the next one by adding 1 to the exponent, t to the 1.6, and dividing the number up front by the new exponent. And then remember, I don't need the plus c here. I'm going to evaluate this from 0 to 2. I'll plug this in the calculator, and I will get 132.736. And this is in feet. So the total displacement here would be almost 133 feet. So let's review real quick here. We found the area of one rectangle by using the formula of the area of a rectangle, length times width. Then we found an area of an infinite amount of rectangles by taking that same rectangle and putting a Riemann sum in front of it, which is the sigma notation. And then the final step was to take that same formula and do an infinite amount of rectangles by using the elongated S. And this process will always give me the exact area of underneath the curve over the region that I'm looking at. Okay, here's some problems that are pretty tough to do that actually I'm going to show you how to do on the calculator. But just to make sure, for example, in the first one that we have the right answer, let's go ahead and try to do this without a calculator. So the antiderivative of this function involves the anti-chain rule. So I got to antiderive the outside, which is 1/3, leave the inside alone, and raise the exponent by 1, divided by the derivative of the inside, so it'll be another 1/3. Again, I don't have to put the plus c, from 0 to 4/3 power. And then I put in 0 and 4/3 and see what I get. So when I put 4/3 in here, I get 3 times 4/3 is 4. 4 minus 1 is 3. 3 cubed is 27. 27 divided by 3 twice is actually equal to 3. When I put 0 in here, I'm going to be careful here, because when I put 0 in here, I actually get negative 1 inside the parentheses. Cubed is another negative 1. And negative 1 times 1/3 twice is 1/9. And so I get 3 minus 1/9, which is 3 plus 1/9, which is like 27/9 plus 1/9, which is 28/9. Okay? That's a lot of work, but I want to show that when we do this on a calculator, this is indeed the answer. Okay, so let's make sure we can antiderive each one of these, even if we don't actually plug it in here. So the next one, the antiderivative of this of secant squared, remember, is tangent of x. And again, I multiply by that 3, evaluated from 0 to 1. Well, this is one of the ones when I put 0 in there, I do get 0. So the answer here is just 3 tangent of 1, whatever that comes out to be. Next problem here, I have antiderivative sine is negative cosine of x, evaluated from 0 to 10. So negative cosine of 10 minus negative cosine of 0, which remember cosine of 0 is 1, so this will actually be 1 minus cosine of 10 if I put that positive 1 out front. And this last problem here, remember the square root of x is the same as x to the 1/2 power. So if I apply the fundamental theorem to this, I get 2/3 x to the 3/2 power, evaluated from 0 to 2. Again, I don't really have to plug 0 in here because this will come out 0, but when I plug 2 in there, 2 cubed, you'll get 2/3 times 2 to the 3/2 power. And we'll see what this looks like, okay? So the nice thing about the Inspire is that you plug it in, just like you see it on the problem. So like here, the first problem, I use the templates button. I find the definite integral, which is the integral with the two bounds, and I plug in my bounds. And I plug in my equation. Remember to plug in dx, so that's the variable used. And you notice I get the 28/9 that I got by hand. The second one I had to be careful of because of the squared. I had to put the squared outside the secant. So you notice here, it'll take a little bit of use with the parentheses to get 3 secant squared x evaluated from 0 to 1. And notice I get 3 times tangent of 1. And the calculator gives it to me as an exact answer. For the last two problems here, you can see here that when I plug it in, I got the 1 minus cosine 10. And that 2/3 times 2 to the 3/2 power turns out to be 4 radical 2 over 3. So learn to use the template button on the calculator to solve definite integrals to find the area under the curve, so that when you have access to the calculator, it saves you a lot of work.